takes place, a specialized subtype of white cells that are part of the innate immune system called dendritic cells carry information from the kidney to the local white nodes called lymph nodes through blood circulation. Here in the lymph node, cells of the adaptive immune system called T cells continually circulate between the blood and lymph nodes and are on constant alert for any sign that the body is under attack. Within the T cells, a small subpopulation called regulatory T cells control how the immune system will react to intruders. Dendritic cells, which are coming from the transplanted kidney, enter the lymph node and begin to mix with the T cells. And as they come into contact with the T cells, some T cells become activated. The body's defense mechanism has been triggered. The activated T cells, called effector T cells, start to multiply and go to the kidney and attack it. Information displayed by the dendritic cells have told the T cells where the intruder can be found. They use the vessels of the body to travel there. T cells attack the kidney and attempt to destroy it as quickly as possible. The immune system is very powerful against foreign intruders. If the immune system is not controlled, the effector T cells attack any unknown organism they find in the body. So if a virus enters the body, the T cells would be alerted to its presence by dendritic cells. Different T cells from those attacking the kidney will attack and destroy the virus-infected cells. The current protocol to control the immune system during a transplant is the use of immunosuppressive drugs. These drugs suppress the immune system, paralyzing it from attacking the transplant. At first, the T cells detect the foreign organ and still try to attack it, but the immunosuppressive drugs prevent this from happening before any significant damage has been done. However, here lies the problem. The whole immune system is paralyzed by the immunosuppressive drugs, so if a virus were to be introduced, the immune system cannot react to it and the person becomes ill. To prevent organ rejection, the patient must take immunosuppressive drugs for the life of the transplant. With a paralyzed immune system, infections are a constant threat. The team at King's College London have developed a way to harness the power of the immune system whilst maintaining the body's capacity to resist infectious diseases. A large sample of blood is taken from the recipient of an organ before the transplant has taken place. From within this collection of cells, a small subpopulation of T cells known as the regulatory T cells are extracted. These cells are responsible for regulating the immune response and decide when and what effector T cells are permitted to attack. These cells are separated, selected for specificity, and multiplied in their millions outside of the body in a flask in a sterile environment. After a few weeks, and just after the transplant takes place, these regulatory T cells are concentrated and injected back into the body. When dendritic cells from the new kidney enter the lymph node, the T effectors specific for the transplant will be inhibited from attacking the kidney by the injected regulatory T cells. But other T cells specific for the viruses retain their ability to fight infection. When a virus enters the body, the immune system is alerted to the danger and destroys them. Such a technique allows the patient to retain the transplant for their entire life, free from immunosuppressive drugs and therefore free from drug-related diseases such as infections.